Hello and welcome to the new unit on simple machines and rotation. I normally start out this unit with a challenge of who thinks they could lift me with one hand, nay, maybe even one finger, and I usually have some kid who volunteers, not knowing exactly how it was going to work, but I usually bring out a long piece of wood like a 2x4 and put another piece of wood as a fulcrum near me, and I stand on that end of the wood, and then I have the other person very far away from the fulcrum and me, and they can usually push down with one finger and lift me up, and that's usually how I introduce simple machines. Simple machines can make a job easier by changing how much force is needed or the direction of the force. So in this case, Archimedes is pushing down and the earth is going up. So his force is being altered in the direction. So Archimedes once said, give me a lever long enough and a place to stand and I can move the earth. Levers can be very, very useful. There's four basic types of simple machines. There's the lever with the fulcrum. There's a pulley, which is a wheel with a rope wrapped over it. There's the wheel and axle, where this is kind of a side view of that, where the rope is wrapped around. You can use a rope or you don't have to use a rope, like the wheel and axle of a car, and an inclined plane, where you've got a sloping surface, and the wedge is kind of included in the inclined plane in my book. They're close. So some basic terminology that applies to all of these simple machines. We've got the input force, which is the force that you apply to the machine. We're going to start off looking at levers just because they're kind of the easiest to look at. And so when you push down on the lever, like Archimedes was doing, that's supplying the input force. Then there's the output force, which is usually the force that's applied to the thing you're trying to lift. So that's the FOUT. So we've got the fin, the input force, and the FOUT, the output force. So again, the output force is usually the weight of the thing you're trying to lift. When you push on a lever, you do work on it. Remember, when we do work, there's two components. There's force and distance. So when we push on that lever, there's the force that I applied and then the distance that my side of the lever moved. So the distance that my side of the lever moved is called the distance, the input distance. I've got a distance of effort. I should have that changed. But the input distance, so the din. So we've got the fin and the din, and the work input, or win, is equal to the fin times the din. So the work input is equal to the force input times the distance input. Work equals force times distance. And then there's work comes out of the machine, and lifting an object and changing its potential energy in this case. And to figure out the work output, that would be the force output times the distance output. So the FOUT times the DOUT equals the work output, or the WOUT. Okay. Now, if no energy is lost, so if all of our input work none of it's converted to heat, then the work input is equal to the work output. This is known as an ideal machine. So if your work input is equal to your work output, then your fin din equals your FOUT DOUT. I'd make a note of this equation because you'll use this one several times. So your fin din equals your FOUT DOUT for an ideal machine. So if there's no friction. But the thing is, while it's theoretically possible, well, technically it's theoretically impossible to get all of our work out that we put in due to conservation of energy. We can never get more out than we put in. So in fact, we'll always get a little bit less. But this is a good approximation. So for what we should get out. You can't get more out than you put in, because that would be like creating energy, and we know conservation of energy says that's a no-no. So, but you can get almost all of what you put in, you can get out in certain situations. So this was the 2x4 experiment that we theoretically did at the beginning of the class. So here's the fulcrum close to me, and I'm heavy. So there's a large output force that's lifting me, and it only required a small input force. But the trade-off was that this side of the lever had to go down a large distance. So while this force had a small force, my input work had a large distance. And on the output side, there was a large output force, but I only went up a little bit. There was only a little output distance that says dr. That should be d out. So we can change the amount of force that's involved and change the amount of distance, but we can't gain more work than we put in. So what we gain in force, we lose in distance. So this was a question on the power lab of a inclined plane, and what I was hoping you guys would come to the conclusion was that you had to push the object up a large distance up the inclined plane, even though you had to use a small force. So you had to do the same amount of work as you would lifting it straight up. So you can't get something for nothing. So anyway, big distance, little force, big force, little distance. So that's usually that's going to be the recurring theme in simple machines. Is it's a trade-off between force and distance. So, and again, this is the ideal machine equation. So simple machines can magnify your output force, but again, it's at a cost. The cost is distance if you gain force. So here we pushed our lever down 1 meter with 20 newtons of force. So we did 20 newtons or newton meters or joules of work in. Okay. And then on the out, we lifted a heavy weight with only 20 newtons, but it only went up 1/5 of the distance. And if we multiply our input times our output, or I'm sorry, if we multiply our force times our distance, 100 newtons times 1/5 of a meter gives us 20 joules, which is the same as what we put in. So this is an ideal machine. So when we're talking about simple machines and magnifying forces, it's useful to talk about the mechanical advantage, and this is known as the actual mechanical advantage, which is the ratio of the output force divided by the input force. So make a note of this equation too. This is an important one, one that you'll use frequently. So Fout over Finn. Now, if your mechanical advantage is greater than 1, what that means is your output force is greater than your input force. So you get a fraction that's greater than 1, which basically means that your input force was multiplied. You got more force out than you put in. If your mechanical advantage, or if your actual mechanical advantage is less than 1, that means that you had to put in more force than you got out. So your force was actually reduced if your mechanical advantage is less than 1. And why would you want that? Well, if you lose force, you gain distance. Again, it's always a trade-off between force and distance. So that is actual mechanical advantage. What's the actual mechanical advantage here? So it's F out over F in. So our 100 newtons is our Fout, 20 newtons is our Fin, so it's 100 divided by 20, so it's 5, which means that our input force was multiplied by a factor of 5. But if we gain force, again, the trade-off is that we're going to lose distance. Again, the recurring theme. So here, what's our mechanical advantage? Well, the output force is what we're trying to lift. So that's 100 newtons, and our input force is 200 newtons. So when we divide output over input, we're going to get 0.5. So notice our mechanical advantage is less than 1, and that our input force was actually reduced. Again, why would we want this? Well, we're going to lose force, but we're going to gain distance, and that is the trade-off. So let's work a couple more math problems. The effort side of the lever is pushed down with a force of 90 newtons for 1.8 meters. This lifted up a box weighing 270 newtons up 0.6 meters. What was the work input? What was the work output? And was this an ideal lever? And what's the actual mechanical advantage? Okay, so I think it's helpful to draw a picture. So we got our input side, which is 90 newtons and 1.8 meters. And our output side, which is 270 newtons and 0.6 meters. So the work input is equal to the input force times the input distance. So it's 90 times 1.8 gives us 162 joules. The output work we go to the output side. That's our force times our distance, so 270 newtons times 0.6 meters also gives us 162 joules. What was the actual mechanical advantage? Well, that's the output force divided by the input force. So 270 divided by 90 gives us 3, which is greater than 1, which means our input force was multiplied, which it was. And the last question is the lever ideal? Yes, it is, because work input equals work output. So that's that example. Let's look at 2 more. So one side of a lever is pushed down by a person with a force of 50 newtons, and a 200 newton object is lifted. If the person pushes down their lever 1 meter, how far does the other side move up? Okay, again, if the lever is frictionless. So we're saying it is ideal. So if the lever is ideal, we can use Fin din equals Fout dout. Our work in equals our work out. So we know Fin, which is 50. We know Fout, which is 200. We know din, the distance input, which is equal to 1 meter. So that goes in there. And that leaves the output distance. So, and our output distance when we solve for the equation is going to be 0.25 meters. So again, we could use this equation because it's an ideal machine. Last problem like this, if an ideal lever is such that when a person pushes their side down 0.8 meters, it lifts a load on the other side 0.2 meters. If the load weighs 100 newtons, how hard does the person need to push? Okay. Now I should have put that this was an ideal lever. I didn't. But it's the only way to solve this is if you assume it's an ideal lever. So we'll use Fin din equals Fout dout again. In this case, we're looking for how hard the person needs to push. So that is Fin. We're given that the person pushes their side of the lever down. So the person's side of the lever is the input side. So that's 0.8 meters. Okay. The load side is what is the output side, so that is 100 newtons, and that goes up 0.2 meters. What is the input force? So solving, we get 25 newtons. Okay, now if there's no friction, then you get a mechanical advantage that's called the ideal mechanical advantage. The book called it the theoretical mechanical advantage. I usually refer to it as the ideal mechanical advantage for whatever reason. And you can figure out the ideal mechanical advantages just by looking at the distances. You don't actually have to measure the forces. You can see what your mechanical advantage should be. So if you have any guesses of what my mechanical advantage should be here's a ramp. If I lift it straight up, it would go up 2 meters, but I have to use a long distance. So if I have a long distance, a big distance, that means I'm going to have a little force. So my ideal mechanical advantage here is going to be 3, the ratio of these 2 distances. And the ideal mechanical advantage, and this is another equation you want to make note of, is your distance input over your distance output. Now note this is flipped as far as input and output goes from actual mechanical advantage. Actual mechanical advantage was Fout over Fin. This is din over dout. So don't make a silly mistake there and get that mixed up. So this is your actual mechanical advantage if there's no friction. Okay, but regardless, you always have an ideal mechanical advantage, even if it's not an ideal machine. You just don't get that much mechanical advantage in the really real world. But you know what you should get. Okay, so what's the ideal mechanical advantage here? I push my side of the lever down 1 meter. My other side, the other side with the load, lifts up 0.25 meters. So that's din, which is the 1, divided by 0.25, which is the dout, and that's going to be 4. So it's going to be 4. And this is going to give me an ideal mechanical. By giving me an ideal mechanical advantage of 4, it means my input force should be multiplied by 4. Will it really be? Probably not, but that's what it should be. So where should I put the fulcrum here? Should I move it to the right or should I move it to the left? If I want to reduce the amount of input force, reduce the amount of force that I apply. If I want to make it easier in terms of the force, do I want to have it close to my force, or do I want to have it close to the load? And if you guessed right, you want to have it close to the load. That gives you a better mechanical advantage. But what happens if you place the fulcrum in the middle? Okay, so now it's not closer to the load or the input force. Well, if you put it right in the middle, it's going to take 100 newtons of force to lift a 100 Newton object. And what would that mean your actual mechanical advantage is? It would mean it's 1. Okay, so your input force is not multiplied or reduced. Okay. What happens if you move the applied force closer to the force that you're applying? As if you move the fulcrum closer to the force that you're applying, well, you get a mechanical advantage that's less than 1. F out over Fn gives you 100 over 500, so 0.2 would be your actual mechanical advantage. So that's what happens if you move the fulcrum closer to the force. Okay, so what I want you to do is do the front, only the front, 7.2.5, and that's it for the notes for today.